Und willkommen back to the lecture. Time to return to this our discussion of enthalpies. When we left, we were wondering, well, I was wondering, rhetorically, whether or not it would be nice to have a standard set of intermediaries to take us from reactants to products, so we could do Hess's law without using random reactions. And that is more or less exactly what we have, thanks to what is known as the standard enthalpy of formation. The little f subscript underneath the delta H means formation, referring to the compound in question being formed from the pure elements. The little degree symbol, the superscript, refers to standard conditions. That's why I called it the standard enthalpy of formation. Standard conditions mean 1 atmosphere of pressure, so air pressure at sea level, so nice enthalpy, open container, and under conditions that humans normally face, and usually 25 degrees Celsius. It might be 20 degrees Celsius sometimes. But because we're dealing with state functions, what that means is that you can, just take your reactants to whatever state they're going to actually be at. Raise them up to the pressure in question, raise it to the temperature in question, or lower. Could be cold, and then you do the reaction at those conditions, or you can go from those conditions down to standard conditions, then do the reaction, then take the products back up to the final conditions. It doesn't really matter because state functions. So long as you're measuring everything carefully and know what you're doing, you can always get from A to B. And that's one of the convenient things. The other thing about the standard enthalpy of formation that we have to take into account is that we're talking about the compounds being formed from the elements under their most stable state and under standard conditions. Sometimes that's simple and straightforward. Like down below, you see nitrogen and oxygen are just gases. Sometimes it's less simple. Carbon, you'll notice here, has 2 subscripts under the state that it's in. It is a solid, and then it says GR. That stands for graphite, because graphite is the more stable allotrope of elemental carbon. You also have diamond, is an allotrope of carbon, but it is somewhat less stable than graphite. So all standard enthalpies of formation involving carbon are calculated from graphite rather than diamond. That is going to be, yes, kind of important in about 5, maybe 10 whole seconds from now. So the standard enthalpy of formation lets us come up with an intermediate step in between the reactants we're working with and the products we want to get to. Because we can do a standard, a normal Hess's law problem like we've been doing, only instead of these random equations we've been working with, we can break, excuse me, we can break the compounds down into their elemental forms. We can sort of pretend that we take all of the reactants apart into their elemental components and then rearrange those elements and put them back together as the products. That isn't how it actually happens, but again, remember, state function. A to B is all that matters. We can make any sort of path we want so long as we get from A to B. So let's work with an actual example. Specifically, the semi-mythical reaction that would take us from methane to methanol by way of reacting with oxygen. So 2 methane plus 1 oxygen molecule yields 2 molecules of methanol. We have methane here on the left and methanol on the right, which we can write down their enthalpy of formation, or their formation reactions with the associated enthalpy of formation. We don't have to do that for oxygen. Oxygen is already an element. And the great thing, or a great thing, or maybe just a thing, about the standard enthalpy of formation formulation that we're working with here is that the enthalpy of formation of a pure element in its standard state is 0. So you could write the delta H of formation of oxygen is just 0. Or you can just say, it's an element, I don't care about it. But methane and methanol we construct from their elements. And so methane is 1 carbon solid graphite plus 2 hydrogen gas yields 1 methane gas, and 1 carbon solid graphite plus 2 hydrogen gas plus 1/2 oxygen gas yields 1 methanol. Remember how I said that Hess's law would give us fractional coefficients. This is pretty much the only place where you're allowed to start with fractional coefficients, because the standard enthalpy of formation assumes you have 1 mole of the product. So everything else is going to be manipulated in whatever way necessary to get you to that product directly. Okay? No messing about. So 1/2 oxygen is perfectly kosher for the standard enthalpy of formation reaction that we're looking at here. Another thing to keep in mind is that we're talking about a delta H, a change in enthalpy. So we're looking at the change in enthalpy going from reactants to products, but the reactants are, by definition, enthalpy 0, which means that the delta H of formation for methane and methanol, as written here, is the enthalpy of the compound in question, sort of. You still can't measure the absolute value and so on, sort of like measuring internal energy. But we can ignore the reactants after a fashion and only care about the products of these formation reactions. Now, before we get to the shortcut that makes enthalpy of formation such a handy device, we're going to go ahead and treat these like the old-fashioned Hess's law problems that we're used to. You look at methane, we want 2 methane on the left in the reactants. We have 1 methane in the product, so we multiply that by -2. We have 1 methanol in the products. We want 2 in the products, so we multiply that reaction by +2. And when we do that, we get a delta H of reaction that is equal to -2 times the delta H of formation of methane plus +2 times the delta H of formation of methanol, or -327.4 kilojoules per mole. Let's go ahead and dive into another example, specifically this one here, working from calcium carbonate to calcium oxide and carbon dioxide. You'll see here that we have the reaction and the 3 enthalpies of formation. So 1 for calcium carbonate, 1 for calcium oxide, and 1 for carbon dioxide. Like I said, we can ignore the elements, actually. So when we look at the reaction, all we need are those 3 numbers. We don't even really need the reactions, the formation reactions, the elements going to the compounds in question. So long as the reaction is properly balanced, the elements will automatically cancel out. It makes it nicely simple to deal with this. But I'm going to go ahead and one last time do a Hess's law problem in order to show you where the shortcut is, how it works, so that hopefully it sticks a little bit better in your brain pans. So when you look at these, you'll see that calcium carbonate, in the formation reaction, it's a product. We want it to be a reactant, so we need to multiply by -1. Calcium oxide and carbon dioxide are both products. They're both already in the products, So we just need to multiply them by 1. The reason it's 1 and -1 is because this reaction is already balanced with coefficients of 1. Otherwise it might be 2 or 3 or whatever. Now comes the neat bit, the place where the shortcut comes in. Let's take a sort of picture-in-picture look at an earlier reaction. Here we have our reaction for methane plus oxygen to form methanol. And you can look and you'll see that for both of our reactions here, calcium carbonate's decomposition and the semi-combustion of methane to methanol, you'll see that the reactants get multiplied by negative numbers, and our products get multiplied by positive numbers. And that is always going to be the case when you're doing an enthalpy of formation style problem. Reactants get multiplied by negative numbers, products get multiplied by positive numbers. The other thing is that we're always multiplying them by the coefficient directly out of the reaction. So methane has a coefficient of 2. It's a reactant, so it gets multiplied by -2. Methanol is a product with a coefficient of 2, so it gets multiplied by +2. And there is a nice, simple way to state this for any sort of Hess's law enthalpy of formation problems, and that is products minus reactants. That's a handy enough mnemonic, but the more formal way to write it, and I think it's necessary to have this formal way because you need to remember those coefficients. The more formal way is that the enthalpy of reaction is equal to the sum of the products minus the sum of the reactants. And you have that letter N in there to show that each product is being multiplied by its coefficient, and each reactant is being multiplied by its coefficient. So it's slightly more complex than just products minus reactants. But the coefficient has always played a role. You've always needed to take advantage of it. You've always needed to use it. So hopefully it won't be too hard to remember that when you're talking about products minus reactants, you're talking about products and reactants multiplied by their coefficients. So when we apply this to our reaction in question, it's going to be the enthalpy of formation for calcium oxide plus the enthalpy of formation for carbon dioxide minus the enthalpy of formation for calcium carbonate, which gives us a total of 177.8 kilojoules per mole. If you think back, quite some time to our lab on the on oxides and their formulas, you remember that you heated up the carbonates, and you were actually able to drive off carbon dioxide. And that's exactly what's happening here. You have to put energy in order to break a carbonate down into an oxide and carbon dioxide. So an endothermic reaction is precisely what we expect. Now let's dive on into another example. This one might be familiar to biology students. I know we're running right up on that boundary of 15 minutes. We'll go a little bit over for this lecture, but it'll be the last one, so I don't mind particularly. This reaction, this example, is the combustion or the oxidation of sugar, glucose, to produce carbon dioxide and water. So what's the delta H of reaction based upon the enthalpy of formation for each of the compounds in question? Well, you need to look those up on a table of some kind. I'd have to give you that on the test. You definitely can't memorize these. There's a different enthalpy of formation for every compound. So the enthalpy of formation of sugar, the enthalpy of formation of oxygen, it's 0 because it's an element. Then the enthalpy of formation for CO2 and the enthalpy of formation for water, specifically of gaseous water, which is different from the enthalpy of formation for liquid water because you have to put energy in order to heat something up, in order to turn it into a gas. So those are different numbers. Now, when you plug those in, it's going to be 6 times the enthalpy of formation of CO2 plus 6 times the enthalpy of formation of water minus 6 times the enthalpy of formation of oxygen, but that's just 0, and then minus 1 times the enthalpy of formation of glucose. And the enthalpy of reaction is negative 1012 kilojoules per mole. You get a lot of energy out every time you oxidize a molecule of sugar. And that is why we use sugar as an energy storage mechanism, because it's really good at it. And that is as much time as we're going to devote to Hess's law problems for enthalpy of formation in any event. But one last thing we're going to discuss is bond enthalpy. You can do a very similar sort of problem using the enthalpy of bond formation rather than the enthalpy of compound formation. It is a handy and rough guide for doing this sort of problem, but it is only a rough guide. It's an approximation. It's not a very close approximation. It's decent, not great, because a carbon-carbon bond is going to be different for the carbon-carbon bond in ethane versus the carbon-carbon bond in propane versus the carbon-carbon bonds in butane, because the entire molecule affects the individual bonds. It's an entire unit, and the bonds are always going to be slightly different. So when you talk about a carbon-carbon bond, it's always going to be different from molecule to molecule. And so this is only an approximation. It's only a rough guide, but it's still pretty decent. It's a good first step. And so what you can do is you can look at something like this, an enthalpy bond formation table, and you can get these numbers out, and all you have to do is you count up all the individual bonds you're looking at, single bonds, double bonds, carbon-hydrogen, carbon-carbon, and so on. And you add them all up, you do the necessary subtraction, and it is almost, but not quite, almost like an enthalpy of formation, a sort of Hess's law problem, with the important caveat that you have to do reactants minus products, because it's just the way they measure and record these bond enthalpies is precisely backwards from the way they measure and record enthalpies of formation. Essentially, measuring the enthalpy of formation for a compound means you are looking at the compound as a product and how much energy is released when it's formed. But for these bond enthalpies, they're measuring how much energy it takes to break the bond. So they're looking at the bond as a reactant. So all they've done is they've flipped the script on you. So that is something that might screw you up when you're doing this sort of problem. Hint, hint, hint. Remember this. When you're looking at enthalpy of formation, it's products minus reactants. When you're looking at bond enthalpies, it's reactants minus products. I am going to throw at least one of those at you because I'm mean, I'm cruel, and that's just the sort of thing I like to do. So definitely remember that. And that is all we have to discuss for this set of slides. I will see you again the next time we do lecture step